In this video, we look at power series. A series of the form series n equals 0 to infinity, a sub n times x minus c to the n is a power series centered at x equals c. Notice, right, that this is a function of x. So we can represent functions as power series. Now, obviously the series will converge for specific values of x. And diverge at other values. So a power series may not give you a function that converges over the function's entire domain. All right, well, notice that if we write the function f of x as this series, then f of c would give c minus c to the n, which is 0, right? Which means that this power series will always converge at c. So a power series always converges at its center. We will examine this further. So if there exists a real number d which is not equal to 0, such that this series converges, then this series converges absolutely for all x such that the absolute value of x is less than the absolute value of d. Now, since this series converges, you must have that this limit is 0. So what this means is there exists some integer n such that the absolute value of a sub n d to the n is less than or equal to 1 for all n greater than or equal to big N. Now notice what we have. The absolute value of a sub n x to the n is equal to the absolute value of a sub n d to the n times the absolute value of x over d to the n. Which means that this absolute value is less than or equal to the absolute value of x over d to the n for all n greater than or equal to big N. Now, if we take a look at this series, it's geometric. Which is going to converge if the absolute value of x over d is less than 1. Obviously, that means absolute value of x is less than the absolute value of d. By direct comparison, this series converges absolutely for the absolute value of x less than the absolute value of d, which is precisely what we wanted. Let's consider the series n equals 0 to infinity, a sub n times x minus c to the n. Furthermore, we're going to let S be a set of real numbers for which the series converges. Without loss of generality, we may take C to be 0. Now, clearly, 0 must be inside S. So S contains some number B, which is not equal to 0. Or, I'm sorry. So if S contains some number B not equal to 0, then S must contain the entire interval negative absolute value of B to absolute value of B. There are two possibilities for S. It could be bounded or it could be unbounded. If S is bounded, then it has a least upper bound. Call it R, which has to be larger than 0. Then we have to have numbers B and S smaller than, but arbitrarily close to R. Which means the entire interval negative b to b is in S for all b between 0 and R. It thus follows that the open interval negative R to R is in S. Furthermore, we notice that S cannot contain any number, absolute value of x, larger than R. But it may contain negative R or positive R. If S is unbounded, then it contains negative b to b for b arbitrarily large. So in this case, S is just the entire real number line. So consider the power series n equals 0 to infinity a sub n x minus c to the n. The series satisfies exactly one of the following. The series converges at x equals c and diverges for all x not equal to c. The series converges for all real numbers. Or there exists a real number R larger than 0 such that the series converges if the absolute value of x minus c is less than R, and diverges if the absolute value of x minus c is larger than R. At values x, where the absolute value of x minus c is equal to R, the series may converge, or it may diverge. Well, this R is going to be called the radius of convergence. So if we consider the series n equals 0 to infinity a sub n x minus c to the n, the set of real numbers x where the series converges is called the interval of convergence. If there exists, I'll write it out for you. A real number r larger than 0 such that the series converges for the absolute value of x minus c less than r, then r is the radius of convergence. If the series happens to converge only at x equals c, then the radius of convergence is 0. And if the series converges for all real numbers, then the radius of convergence is infinite. Well, let's take a look at the series n equals 1 to infinity, negative 1 to the n over 4 to the n times n times x minus 5 to the n. We want to examine, or we want to determine the interval of convergence. Well, we studied a test to determine when a series converges, right? We studied the ratio test. So let's take a look at this limit. All right, let's simplify this. We'll have negative 1 times x minus 5 times n all over 4 times n plus 1. We can factor out an absolute value of x minus 5. Right, then what we're left with is the limit of n over 4 times n plus 1. So we get a quarter times the absolute value of x minus 5. However, to converge, that limit had to be less than 1. So what this means is that the absolute value of x minus 5 has to be less than 4. Right, so by the way, this 4 would be the radius of convergence. Well, this means that negative 4 is less than x minus 5, which is less than positive 4. If we add 5 to everything, we get 1 less than x, which is less than 9. Well, at those endpoints, 1 and 9, this limit gives us 1, right? And the ratio test is inconclusive at 1. It could converge or diverge. To determine which it does, we look at each individually. So if we have x equals 1, let's see what kind of series we get. Once everything's simplified, we get the series n equals 1 to infinity of 1 over n, which diverges because it's the harmonic series. So the series diverges at x equals 1. Well, we do the same thing we look at x equals 9. So at 9, we get the series n equals 1 to infinity of negative 1 to the n over n, which converges, right, by the alternating series test. So it converges at 9. Therefore, what we say is that interval of convergence, right, 1 to 9, open at 1, closed at 9. Next, let's look at this power series. Well, again, we're going to use the ratio test. So we're going to examine that limit. Simplify it. We're going to get x squared over (2n plus 2) times 2n plus 1. So absolute value of x squared times the limit as n goes to infinity of 1 over 2n plus 2 times 2n plus 1. Well, that equals 0. And notice that this is less than 1 for all values of x. Right? This limit is always going to be less than 1. So the interval for this series is all real numbers, negative infinity to positive infinity. Now what we'll do is find a power series expansion for the function f of x equals 1 over 1 minus x squared. In other words, we're going to represent 1 over 1 minus x squared by a power series. Well, first, recall that the geometric series n equals 0 to infinity of r to the n is equal to 1 over 1 minus r for absolute value of r less than 1. Therefore, what we can say is that 1 over 1 minus x is represented as the series n equals 0 to infinity of x to the n for absolute value of x less than 1. And notice what this implies. 1 over 1 minus x squared would be the series n equals 0 to infinity, x squared to the n for absolute value of x squared less than 1. So what we have is 1 over 1 minus x squared is the series n equals 0 to infinity of x to the 2n for absolute value of x less than 1. So let's suppose that the series n equals 0 to infinity a sub n x to the n and the series n equals 0 to infinity of b sub n x to the n converge to functions f and g respectively on a common interval. First, the series n equals 0 to infinity of a sub n x to the n plus or minus b sub n x to the n will converge to f plus or minus g on the interval I. Second, for any integer m greater than or equal to 0 and any real number c, the series n equals 0 to infinity c x to the m a sub n x to the n will converge to c x to the m times f on the interval I. Three, for any integer n greater than or equal to 0 and any real number c, the series n equals 0 to infinity a sub n times cx to the m to the n converges to f of bx to the m for all x such that bx to the m is in I. All right, well, let's take a look at the function f of x equals 3x over 1 plus x squared. And we want a series expansion for this, right? So notice we can write it as 3x over 1 minus negative x squared, which is 3x times 1 over 1 minus negative x squared. Well, then this will be 3x times the series n equals 0 to infinity of negative x squared to the n, which is 3x times the series negative 1 to the n, x to the 2n, so this will be the series negative 1 to the n, 3 times x to the 2n plus 1. And this was, of course, all for x being less, absolute value of x less than 1. Let's now look at 1 over x minus 1 times x minus 3. Well, what we're going to do first is write this as a partial fraction decomposition. Right? And I'll leave it to the viewer to verify that what we get is 1/2 over x minus 3 minus 1/2 over x minus 1. Which we can write 1/2 times 1 over x minus 3 minus 1/2 times 1 over x minus 1, which we can now rewrite as 1/2 times 1 over 1 minus x minus 1/2 times 1 over 3 minus x, which can be written as 1/2 times 1 over 1 minus x minus 1/6 times 1 over 1 minus x over 3. So 1/2 times the series of x to the n minus 1/6 times the series x over 3 to the n. And this is for absolute value of x less than 1 in both cases, right? So we get the series n equals 0 to infinity of x to the n divided by 2 minus the series n equals 0 to infinity x to the n over 6 times 3 to the n. And again, this is for absolute value of x less than 1. So this will be the series n equals 0 to infinity of x to the n over 2 minus x to the n over 6 times 3 to the n. You can factor out an x to the n over 2, right? So we'll be left with 1/2 minus 1 over 3 to the n plus 1, then all times x to the n over 2. for absolute of x less than 1. Right? I do need to clarify that if we look at this summation here, right, this would give us that the absolute value of x minus 3 would have to be less than 1, which means that absolute of x is less than 3. Well, if absolute of x is less than 1, it's guaranteed to be less than 3 as well. So that's why we stuck with the absolute value of x less than 1 there. Oops. So let's suppose that the series n equals 0 to infinity a sub n times x minus c to the n converges to a function f on the interval I. Then, if we take a look, f prime of x, this is going to be equal to the series n equals 1 to infinity d dx of a sub n times x minus c to the n, which is equal to the series n equals 1 to infinity of n a to the n times x minus c to the n minus 1 for x and I. And number 2, the antiderivative of f of x is equal to the summation n equals 0 to infinity of the antiderivative a sub n times x minus c to the n dx, which is some constant, plus the series n equals 0 to infinity of a sub n over n plus 1 times x minus c to the n plus 1. And this is for absolute value, for x in I. So what this is saying is we can do term-by-term differentiation and term-by-term antidifferentiation of power series expansions. We'll find a power series expansion for 1 over the quantity 1 minus x squared. We'll notice that 1 over 1 minus x squared is equal to the derivative of negative 1 over 1 minus x. No, it is, positive 1 over 1 minus x. Therefore, this would be the derivative of this series, which is the series n equals 1 to infinity of n x to the n minus 1 for absolute value of x less than 1. We can rewrite this to be n equals 0 to infinity of n plus 1 times x to the n. Right? So we can shift our index if we like. So either one of these would be acceptable. Let's look at a series expansion for the inverse tangent of x. Well, note that inverse tan of x is an antiderivative for 1 over 1 plus x squared dx. So what we can say is the inverse tan of x is equal to the antiderivative of this series for absolute value of x less than 1, right? So this is going to equal the series -1 to the n times x to the 2n plus 1 divided by 2n plus 1 plus some constant. And this is for absolute value of x less than 1. Now we know the inverse tangent of 0 has to be 0. So this implies that this has to be 0. Well, this series, right, is just the sum of a bunch of zeros, so that's just 0. So that means that c is equal to 0. So a series expansion about 0 for inverse tangent of x is the series n equals 0 to infinity, -1 to the n times x to the 2n plus 1 all over 2n plus 1 for absolute value of x less than 1.